Okay, YouTube, in my last set of videos, we explored arithmetic sequences of numbers. That is to say, I guess sequences that have a common difference between them. Things like, maybe 3, 6, 9, 12, so on and so forth. But things that are constantly adding on some constant value between the terms. What we're going to look at here is geometric sequences. And geometric things are, I guess, if you would ask me, somewhat similar with respect to how they behave, but different in terms of how it is that they're behaving that way. So that is to say, if we were to have a sequence of numbers like 1, 5, 25, 125, we could go one more here, we go 625, and so on and so forth, you would see something that has a common factor. And so instead of a common difference, what we're seeing here is that we're taking these numbers and we're quintupling them every time. We're taking them times 5. So when we see this constant multiplication by a constant or common ratio here, then what we get is what we refer to as a sequence that is geometric. And so you can see the geometric things, kind of like this picture here. We said, take the total number of squares times 5 here. You can see this. So we have 5 squares, 25 squares, 125, 625, so on and so forth. So the definition of a geometric sequence is this. We say that a geometric sequence is just a sequence in which each term after the first is obtained by multiplying the preceding term by a fixed non-zero constant. So kind of like we multiplied by 5 every preceding term up here to get the next term. So we say that the amount by which we multiply each time is called a common ratio of the sequence. And so the common ratio is denoted by the letter R, kind of like we use D for the common difference when we looked at arithmetic sequences. So we say that common ratios are, we find these by dividing any term after the first term by the term that directly precedes it. So that is to say, for instance here, in the following examples, we could find the common ratio by taking the second term and dividing by the term before it. And so for instance here, 5 minus 1, we would get 5. But what that's telling us is that that's the common factor, the common ratio between each of these two terms. So our common ratio here is 5, but only because every term, like 625 divided by 125 is 5, but every term divided by the term before it is 5. So for instance here, 8 divided by 4 is 2, 16 divided by 8 is 2, 32 divided by 16 is 2. So we must be doubling here. Here, interesting story is when we divide this negative 12 by a positive 6, we actually get a negative 2 as our R value. So when you see that we're multiplying by a negative 2, and then we multiply by another negative 2, and we multiply by another negative 2 here, you can see that the signs are alternating on our terms here. And so just like in that one, our last one here, if we were to take a negative 3 and divide it by a positive 9, we get negative 1/3. So you can see that we're multiplying by a third every term to get the next term, and it's alternating signs. So really quickly here, this sequence that we had listed here, this 5, this powers of 5, what you see is it is graphed here. And so we have a sub n and n, where this is our term number, and then we have our term value. But you can see our first term here is 1. Our second term here, our first term, this would be 5 to the first, is, we have 1, and then we had a 5 here, and then we got a 25, and then we got 125. This really, when you look at geometric things, because we're multiplying every time by a constant number there, then what we get is an exponential function, okay? And so we would say that this here shows a partial graph of the first geometric sequence in our list, and that the graph forms a set of discrete points lying on the exponential 5 to the x minus 1, or in other words, the graph of the exponential function where it's been shifted right 1 from our original goes through here, goes through 1, 5, just shift everything to the right one, that's this graph. And so what we're going to say is that geometric things are just exponential functions whose domains are the set of positive integers. So for checkpoint 1 here, what we're going to do is this. We're just going to write the first 6 terms of a geometric sequence with the first term is 12 and a common ratio of a half. So really easily done. What we could say is, well, we know our first term. And so our first term here is 12. What would be the value of our second term? Well, because our common ratio is a half, we're going to take this times a half, we would get 6. And another good way to prove this is to take our 6 here and divide by the term before it. 6 12s would give us this half. So take this times a half, we would get 3, would be our third term here. Our fourth term would take that 3 times a half, we would get 3 halves. So that's our fourth term. Now if we were to take 3 halves times a half, we would get 3/4 would be our fifth term, and then our sixth term here in this geometric sequence would be 3/8, which would be 3/4 times a half. And so in the next video we're going to look at how we can write the general rule for something that is geometric. Cheers.